over the past several centuries, we, humankind, have been very good at getting hydrocarbons out of the Earth's crust. We've become insanely good at finding them, whether they're beneath the middle of the ocean or the middle of a desert, and then using big drills and pipes and all sorts to extract them. So we have a really impressive set of tools and technologies for doing this. But, as we all know, this has had some pretty bad consequences. However, what if we could take these technologies and either use them to put carbon back underground, or perhaps search for a guilt-free source of energy within the Earth? These are the two topics that we discuss today with our guest, Rūta Karolytė. Ruta is a researcher at the University of Oxford, and she first takes us through carbon capture and storage. So this is, I think, something that will be familiar to many, but Ruta really goes into the details of how this carbon sequestration works, how we can take carbon directly from the air or from chimney flues and then bury it safely deep underground. The second thing that we discuss, I think, is a bit fresher. So this is just starting to appear on the radar now. It's June 2023, and it's the idea of hydrogen. Okay, so hydrogen is not new, but for a long time, very few people thought that hydrogen occurred naturally within nature. They thought that you either had to create it from water by electrolysis or maybe by steam reformation of methane, but it just didn't occur on its own as H2. Now, Ruta takes us through some, frankly, fascinating evidence that it does exist naturally and possibly in very large quantities within the Earth. And this is exciting because this could be a cheap and copious energy source. And it's not completely academic. Ruta is actually also a prospector. She is part of a small company that is going out and looking for hydrogen within the Earth. So this is a really optimistic and enlightening story. In fact, along the way, I learned things like that there's a completely other form of life that I wasn't aware of on the Earth. So look out for that. Without further ado, I'm James Robinson. This is Multiverses. So this is a very optimistic and enlightening conversation. I learn a lot of things. I learn about an entirely new form of life that I'd never heard of. So hope you enjoy this as much as I did. I'm James Robinson. This is Multiverses. Hi, Rūta Karolytė. Thanks for joining us.
Hi, James. Very nice to be here.
So geology is not what first comes to mind, let me put it like that, when people are thinking about the kind of skills that we need to combat climate change. Although many people think a little bit harder and think, actually, there's something here with carbon sequestration, which I've heard about. And I want to talk about that first, and then maybe after that we'll talk about something that I don't think many people will know about, which we'll kind of maybe unpack later as a kind of we'll leave that thought hanging. But yeah, let's first talk about carbon sequestration. What is the role of geologists like yourself in putting carbon back into the ground? I guess there's a clue there.
Yeah, no, I think that's a really interesting question, and in terms of thinking about geology, what it can do, and I think I quite like the sort of a thought that I guess a lot of people have, that it's sort of hard to say like where geology comes into the picture. When I was sort of choosing to study geology and I was at school as a teenager, I was sort of like very anxiety ridden about the environment and climate change and ecosystem collapse, as I think even more people these days who are young feel that way now. And I really wanted to do something about it. Like I really wanted to do something environmental. I had no idea what it would be. And so I thought, like, if I study the earth and how it works, probably, I might be able to figure out what to do. So it appeared to me that, going and studying geology and how the earth works would be like an obvious first step. and yeah, so I went into it without really knowing kind of what I was going to do, but for like, I'll just learn, how things work naturally, and then we can maybe think about how to help it. But yeah, in terms of kind of its role, like, I guess, in terms of climate change, like, geology also does have like a lot to answer for, because
Yes.
essentially through our sort of exploration of the resources, we have caused climate change, or we have caused all kinds of habitat and environmental destruction. But at the same time, like, sort of the geology and the raw materials that we have on the planet is essentially like all we have to work with. And like, very understandably, as society evolved, we have like used those things for building materials, metals, and all kinds of things to kind of build technology and everything that we have out of it. And that has caused a lot of problems, as well as actually like prosperity. And so yeah, I think there's kind of like two kind of main roles of it in the future. Like, I think it will have to obviously continue playing a role, because we will continue needing all the raw materials for all the different technology or whatever we might decide to do. Maybe like until we start mining asteroids or something, but like, we'll have to continue kind of working with what we have in the subsurface a lot of the time. So yeah, one of the roles is like finding ways of using these resources in a kind of smarter and better and more effective ways and more sustainable ways. And then a second big part, which is, the carbon question, is perhaps undoing some of the stuff that we have done without thinking too hard about it. So the fact that we have so much CO2 in the atmosphere is primarily because we have just taken it out from the subsurface and put it up in the atmosphere. And so I think in terms of the mass balance, and it does make a lot of sense to think that to deal with this problem, we may as well consider putting it back in the subsurface, where it came from. And so, yeah, there are sort of many different kind of ways of thinking of CO2 sequestration, but geological CO2 sequestration is something that I work on. And yeah, the simple idea of that is that we often have industrial processes that produce CO2 as a byproduct. And so we will, and now as is, we will say burn fossil fuels to produce energy, or we will have all kinds of different manufacturing processes that produce CO2. And the CO2 is just vented to the atmosphere. So the idea is to, instead of doing that, to capture the CO2 at the point source, process it, sort of clean it, and then inject it back in the subsurface underground for geological storage. So sort of essentially go through this process of taking a fluid out, which is some kind of hydrocarbon fluid, taking it from it what we need, and then putting CO2 back underground. Yeah. So that's the geological CO2 storage.
Yeah, and I think it's worth pointing out here that the way you phrase it doesn't necessarily sound like, one might think, oh, well, how's that going to take carbon out of circulation in the atmosphere, I guess. But depending on how you play it, you could be growing a lot of biomass. So growing, I don't know, things that you then burn, basically. And obviously in the growing process, those plants are taking carbon out of the atmosphere and sort of building it into their hydrocarbon structures, their leaves, their stalks, etc. You burn that, and then you capture as much of the CO2 from the flue gases as you can and put that underground. And that creates like a kind of net negative, I guess, movement of carbon from the air into the crust. Kind of almost a little bit counterintuitively, because you're burning something, but when you think about the whole loop, it's taking stuff out of circulation. I guess that's called BECS, if I'm getting my acronyms right here. Yeah, so tell us a little bit more about this. I mean, how effective? I mean, maybe let's start before we sort of literally dive into the ground. If we start. If we start on the kind of flue gases, like how good are we at extracting carbon from, or CO2, I guess, from those flue gases? Like how much escapes and how much we manage to take out?
Yes, I think the efficiency of extracting the CO2 from the flue gas is pretty high, and sort of the kind of the field of development, the research is really at like bringing down the cost, because obviously this process, well, in terms of enabling CO2 storage, really what's happening is that, you know, we have industries that operate the way they operate now, and adding on this addition of, then you also have to like capture the CO2, extract it, and it just is an added cost, and there's no like associated sort of financial gain to it, right? So other than, you know, like the potential incentives from various, like for carbon tax or things like that, so sort of legislative incentives of removing carbon. And so yeah, the big kind of challenge is to make it as efficient and cheap for capturing and extracting the CO2 from the flue gases. But still, it's essentially, it is always an added cost. You know, it is, I guess, like as something, as an industry, it is not really like a product that you're producing that somebody wants to buy necessarily. It is actually like a kind of waste management program that we have just never implemented, and now we have to bear the cost of implementing it. and sort of no one wants to really do that, because, you know, very happily we've been venting it to the atmosphere. But it is kind of sort of somewhat similar to, you know, just like I don't know, like pouring out sewage into the street in like medieval London or something. It's like eventually somebody has to put in the infrastructure of dealing with it.
Yeah. This is the classic tragedy of the commons, right? There's no cost to just doing that unless we create some kind of carbon, and there are, you know, plans already for, you know, different sorts of prices on carbon, whether it's taxes or credits or whatever. But I guess, yeah, as you say, there's very little incentive for doing this outside of that, right? This is like an outside cost. I suppose there's the other thing worth mentioning, apart from those carbon credits, is a lot of companies sort of are actually looking to do these sort of things, even if it hurts the bottom line, which is surprising. But it does seem to be that people are investing in this. Yeah. So yeah, that's an interesting point, that it's not so much the efficiency. I think the efficiency, I looked this up recently, so it's somewhere around 90%, which that sounds pretty good. And then you could make it higher, but it's going to cost a lot more. And in some ways, what you really need is just to make it as cheap as possible. So it's kind of like a no-brainer to add this on. But yeah, maybe then take a sort of, once. And I guess the other expensive thing that we're going to talk about is what you do with that carbon once you've kind of concentrated. So you take it out of the flue gases. What happens next? Do you have like a lot of gas? Like you have a lot of gas, I guess, right? Or is it in another form? What do we do with that?
Yeah. So yeah, before I go on the storage part, I guess I want to make a comment of, kind of, because it's this expensive thing that we're going to add on to some sort of industry. Like, I think the question has really been of like, where exactly does it make sense to do this, you know? And that has just been changing with time. And so like when this all started, there, like this idea of, say, green fossil fuels has been sort of quite popular, where you could just continue using fossil fuels to generate energy and then capture the CO2 and store it underground. And then as kind of, that's been criticized widely and is sort of widely accepted in the CO2 sort of sequestration community, that probably that's not the best kind of way to move forward, because essentially you're just enabling like fossil fuels to continue, but with like way like larger cost, while we have like way better renewables for, you know, like technologies like renewables for generating electricity. So something like that, you know, could work technically, but is it the most optimal solution? Probably not. And so then the question is like, where does it actually fit? Where is it really needed? So I think some things that kind of really stand out is processes where we don't have like an alternative, like a viable alternative with renewable energy. So things like various industrial sort of applications, for instance, making cement. So making cement involves taking limestone that has carbon in it and heating it, and a byproduct of that is CO2. And sort of cement is just like this super useful material that we just can't stop using. And there's a lot of, industrializing to do in various countries still. So we will just continue, and it accounts to something like 8% of total like global emissions. It's like a really huge part. Yeah. so say like really targeting these big industrial kind of processes and say capturing CO2 in a cement plant, I think makes a lot of sense. And so that's mitigating the emissions that we kind of have to, we will have to sort of have them. We don't have a better idea about it right now, other than say like refusing to build new houses for people, which is not really gonna go well. And then another part is what you mentioned, so things like BECCS, where it actually offers the sort of opportunity of negative emissions, right? Where again, like with various other applications, we can think about reducing the emissions, or perhaps reaching zero emissions, having something like that as net zero. But in terms of negative emissions, it's then like quite hard. And because we have so much CO2 already in the atmosphere, and we will kind of continue. There will continue being applications, say, as aviation and things like that will be like hard to phase out entirely. We will continue like having some kind of emissions, and so like to counteract them and have actually negative emissions. Whereas you say, we can grow biomass, we can burn it, and then we can store the CO2 underground. Is a sort of in terms of strategies that various countries have of reaching net zero. BECCS has been like such a huge part of the commitment, say for in IPCC and the Paris Agreement, the United Nations. Like very many countries put so much weight on BECCS just because it's very hard to balance, your sheet otherwise. And to some degree, like I think there has been an overcommitment to BECCS, and it's like, okay, well, we're gonna get rid of 50% of our emissions by BECCS at some point. And we'll think about how to do that later, and probably not invest in research for a long time. It does have that like really great potential, but sort of exactly the scale of it, I think, sort of remains to be kind of seen, because on paper, like of course you could grow a lot of forests technically and then burn the biomass and then sort of store the carbon, but how it plays out in sort of real world and kind of where you're going to have these managed forests and how it's going to be legislated and managed, and is it actually going to interfere with natural habitat, and are we going to end up in these sort of situations where kind of we create like this legislative framework that encourages, say, just replacing natural woodland with some kind of managed forest, and then sort of saying that that's good for the environment. Like there are a lot of, I think, things to kind of do more work on and research of how exactly this can be something that's like it doesn't end up having negative consequences to kind of the scale, I guess, that it's proposed.
I kind of have the same reservations about BECCS, and I think back to the very first podcast I recorded with Casey Hanmer, who is in some ways trying to do something similar. They're trying to create hydrocarbons, but in a carbon neutral way, possibly carbon negative, because they could sort of store some of the hydrocarbons that they create, probably not geologically, but as materials. But yeah, so here's kind of one of the things that stood out for me from that conversation was that photosynthesis is not super efficient compared to PV. And we know, photovoltaics are about, 20 to 30% efficient. We might be able to push them a bit higher, but I think probably the focus should be just on bringing down costs. Although there's lots of promise in perovskites and things like this that will probably increase the efficiency. But in any case, like 30%, 20 to 30% efficient is pretty good for something that's so simple and cheap to produce. Now, his point was, PV is about 1,000 times more efficient at converting sunlight into energy than plants. Now, plants obviously convert sunlight very directly into hydrocarbons, which is pretty cool. And you need to do more work with PV. And Casey's idea was, or is, that will basically strip out carbon dioxide from the air, will also get moisture from the air so that we get water. We'll electrolyze that water, again, all using PV. And we'll use this all to make methane. And there's other people with similar plans. And yeah, it involves a lot more work, but it should be orders of magnitude more efficient in terms of like land area for the amount of hydrocarbons that we can create compared to BECCS. So yeah, that just makes me think, well, what? Clearly BECCS is important, and it's kind of an easy thing to get running. And we can use it like with a lot of existing kind of power stations and things like that as well. We can just grow this stuff, put, I guess, the correct carbon, like the correct technology in the flue to extract the carbon. And so I think it, merits certainly investment, but maybe air to fuel is a little bit underinvested. And one final thought, like that just struck me the other day, is like, if plants were more efficient, they would be darker. They would be black, right? If they were better, right? Like, and yeah, nature's done a wonderful job, but it's not just optimizing for them to convert energy into, sunlight into hydrocarbons. Like it's balanced a lot of things. Whereas PVs, we've designed that to do just that. So I don't know, a bit of my kind of musings on this, but I don't know, if you have kind of similar, thoughts or disagree with any of that.
Well, yeah, I mean, I would certainly agree that, like producing energy from PV and then just using the electricity will be way, more efficient than growing plants and then using that for energy somehow. But I guess like the fundamental difference there is the kind of, I guess, like because the sort of choice of biomass here is not because it's extremely efficient at providing you energy, but because there is that aspect of it where you can take the carbon, capture the CO2, and then store it somewhere. And so if we're just using PV for energy, that's great because it's just renewables. But if we're also like producing some kind of hydrocarbon from it, from say air and that energy, I guess like the question I have is sort of how does that help with removing the carbon? It is like I guess if we just surely like using electricity, like I think the thinking here is that at some point where we have such abundant electricity that we just don't know what else to do with it, and we can also make sort of hydrocarbons, but like I guess like sort of I don't feel like there's any shortage of hydrocarbons right now that we need to like right now make them in more expensive or more strange ways like that. And essentially like when you make biofuels, you're kind of taking the CO2 out of the atmosphere, you're putting into fuel, and then again you're emitting it, so it's a sort of like it's kind of a single loop, and then it's back out again rather than you remove it from the system. So I guess like I don't see it so much as like a sequestration technology, more just alternative ways of making fuels.
Yeah, I think that's right. It's carbon neutral if you use PV as part of an air to fuel process, but it's not necessarily sequestering. But you could, I guess, do that, but it probably would work quite differently to how it works with the kind of flue stack stuff, or maybe not actually. I guess it's kind of similar. Like you could imagine doing an air to fuel thing that kind of combines direct air capture. So you take some of your carbon and you combine that with hydrogen from electrolysis to create methane. That's something you burn again. That part's carbon neutral. But you take some of your carbon and you just, you compress it. You do the things we're going to talk about in a bit, and you put that back into the earth. So I think it could, like, it seems like it could work, and the big kind of advantage is just like it should be a lot more efficient than just growing plants. And then you get around the problems that you mentioned of, are we just going to end up with lots of like monolithic monoculture patches, which doesn't sound so great. Whereas,
Yeah.
the alternative might be, let's rewild a lot of areas, and of the, let's say, of the every 100 acres that we would have had as kind of monoculture, we'll have like 99 acres rewilded and 1 acre with like a PV plant, and that might be the same, producing the equivalent amount of energy. But I just mentioned something here that we've not really talked about, which is direct air capture, which is kind
Yeah.
of like, yeah. So tell us a little bit about that, because this is another place where carbon sequestration is kind of key.
Yeah, so I guess like yeah, it is sort of serving the same purpose then as BECCS, but instead of using plants, then we strip CO2 from the air, and I guess yeah, that'll be the same as like what are we going to do with the CO2? Are we going to make fuels, or are we going to just straight up store it somewhere? And so yeah, so that again, that technology. There's a lot of research in it, and again, like it is effective. It is just very expensive in terms of the energy need. I think it works best where you can have like essentially free energy, like in geothermal kind of areas where you can have like energy from heat. So say in Iceland or places like that, the costs are significantly lower. But I think right now it is in this kind of R&D stage where we are sort of developing ways of doing it and trying to bring down the cost with like essentially the same view in mind that, in the future, we will like the primary use of it really is for negative emissions. We will just deploy it for taking CO2 underground and putting it off the atmosphere and putting it underground. And I guess like in sort of my understanding of say BECCS and direct air capture is that say direct air capture doesn't really like then produce energy, it just consumes it. BECCS has some kind of purpose of producing energy, but in some way it's almost like a byproduct. Like both of those ideas are really primarily about capturing carbon with some kind of efficiency from the air and then storing it. And so I think like this kind of world where where we have renewables and solar to such sort of degree that we have like so much electricity that essentially like that just developing solar to that level like solves so many of our problems already. And so like we have like that will be a way cheaper and better energy than the energy we get from burning this biomass. And so the role of burning the biomass will kind like in terms of efficiency, that will no way compete with solar, but yeah, the purpose of it will be just so we keep taking the CO2 out of the atmosphere, and the same with direct air capture. And then both of those things kind of then really fit. And I guess like hopefully like if we have this kind of situation where solar is so cheap, then direct air capture suddenly becomes something we can do, and then we can do away with like trying to plant forests. Yeah, that would be pretty good. And so I think like, and even like then using like air to fuel is essentially I think in the same world where energy is just from solar, and we don't have to worry about this anymore, and we're just thinking of new ways of putting CO2 underground or maybe utilizing it in some kind of ways.
I think that's right. Both the air to fuel and the direct air capture, they kind of live and die by energy becoming so cheap that you can just throw it away, right? And there is really good reason to think that we're on that path with renewables. I'm hoping to talk with Rupert Way, who was an author. He's at the Oxford Martin School, so he's based not too far from you, where they kind of look at the economics of all these things, and they looked at just how much the price of renewable energy had come down over the last few decades, and it had exceeded every prediction. And they were like, well, why is this? And it's just that the learning rate with renewables has been so great. And I think partly that's because renewables are these, solar in particular, are these kind of small units that you produce in the millions and millions of quantities. And every time you build a factory, and you're building many, many factories, and you're, also iterating those factories, that gives you like a process of, an ability to improve things, and that creates this learning rate for something like every doubling of your installed solar capacity, the costs fall by, I think, maybe 15% or more, which just means that we're on a kind of a massive downward trend. and that might make things, or if it does continue, it will make things like direct air capture and air to fuel not just economically feasible, but really cheap in terms of air to fuel. I think like it could be cheaper to do that than to create your fuels from in the current ways, at least. I think worth mentioning though that the reason why it makes sense to start with adding carbon sequestration to BECCS plants and as you said, like existing concrete production facilities, is that, and this is an obvious point, just the CO2 there is in super high concentrations, whereas in the air we're in like the 400 parts per million. So you have to go through, you just have to churn through a lot of air if you're using direct air capture. And that's just, you think about those fans turning, right? And the kind of, pulling off these just few molecules in every 1,000 or something, then.
But like I think all of this tech has its place kind of in the sort of timeline of how we go in decarbonizing and when it should be applied. And certainly, where say with cement, I think it's like just super obvious. We have these plants and we need concrete. We can continue needing it. We will be producing it. And right now, it's 100% of it is just being transported to the atmosphere. And so, like, it just makes a lot of sense to just not do that, to capture the CO2 and store it. And it's something that we can do immediately. It's just, like we can do it right now and make things way better immediately. And then I think like it's super important to work on all technologies like direct air capture, because eventually, when we decarbonize all the easy things, and it's just kind of, it's always like the biggest wins are the easiest ones. So say like in the UK decarbonization, we just shut down all the coal plants. That was quite easy. Also, they were like really old and kind of like reaching the end stage of their life, and that sort of decreased the emissions quickly, like by a lot. So you can meet your targets like that. But also, they were just out. They're going out anyway. And so you keep kind of doing that, and we'll like, continue like with things that are like a bit more obvious, and say like capturing CO2 from cement plants. And eventually you'll get to a place where we still have a lot of CO2 that we already emitted. We still have emissions that are really hard to kind of prevent, like aviation, for example. And then you will like really need your direct air capture. And so hopefully you have been doing research and R&D into this for like last 30 years. So then we have these pretty efficient machines by the time we really need to deploy them. So that's kind of like where I think, say, direct air capture comes in, and maybe air to fuel technology, while say some of the kind of geological CO2 storage and the stuff I've been kind of working on, like I feel this is just like we can do it right now. Like there's these things we can do right now, and it'll be better right now. It doesn't depend on us developing anything new.
Okay, that's cool. I think that's a good like lead in, because we spent a lot of time sort of above the ground, but sort of So how do we get this? We've taken the flue. We've extracted carbon dioxide from flue gases. Like, how do we get it underground? What is that process?
So again, the idea of this is kind of quite simple. You have CO2, you pressurize it, and then you use these wells. It's kind of very similar process, exploring for hydrocarbons, but kind of reverse. You have wells drilled into the subsurface, and you can inject fluids in there, and sort of they will be within the pore spaces of rocks. And I guess I think a sort of a good way to think about where is it that we're proposing to put this gas, and it doesn't sound super intuitive, like often it sounds to people that we're just gonna like create these like pressurized chambers underground, and it's like a really kind of unstable, crazy situation. Like, why do you want to pump things underground? But like a good way to kind of think about that is to maybe like think about what like already is underground, like what is it that we're actually dealing with in the subsurface. And so we have sort of kilometers of rocks in the subsurface that all of them have like a lot of pore spaces, so these kind of little holes and fractures in them that are interconnected. And so everything below the surface, all the rocks have actually like a lot of volume in them that's not just rock, but there's open space, and all of that space is filled with water. So like everything is water saturated, and there's kind of like a surprising amount of water underground. Like I mean, it's more. I think people associate mostly it with sort of, so we know about groundwater in aquifers that we use for drinking, and sort of that tends to be kind of more shallow water. But yeah, this kind of shallow fresh water is like only like a fraction of water that we have in the subsurface, and so most of it is actually quite saline, because if when you keep going deeper, the water is still there, but it sort of moves slower, and because it moves so slow, it has more time to sort of dissolve various minerals from the rocks, and it's like salty and briny, and not really good for any sort of applications like drinking. So yeah, so the whole of subsurface is just this kind of hydrological system that's saturated with water, and there's a lot of space in it. And yeah, like in some of the areas which is suitable for, say, injection, it's something like 30% of total volume of the subsurface is just like these spaces with water. And so like yeah, like the whole of the surface is already like this kind of pressurized hydrological system, which is mostly water, but also like it contains all kinds of other things in it. So there's already like a lot of gases dissolved in this water. There's like naturally nitrogen dissolved. There's CO2 that's naturally already also dissolved there. There's like methane, and in some parts, this is also like where we have hydrocarbons and oil and gas. It is essentially just more water, but with like a little bit then of organic matter, and then there's hydrocarbons within this water that that we'll kind of drill into and extract. And so yeah, like the subsurface naturally is just like this kind of multi-phase fluid system. There's like oil and gas, and some of the gas is dissolved, and some of the gas is in the gas phase, and yeah, there. And so the idea is that we can inject CO2 into this water, and it will dissolve in it. It will dissolve in it. We can kind of predict how much you can put in a subsurface, and some of it will dissolve, some of it will be stored in a gas phase. And yeah, we're targeting sort of these really porous rocks, sandstones that have a lot of space filled with water, and also in particular the areas that are suitable, they would have seal rocks, so some kind of really impermeable rocks like shales on top. So then the gas that is there in a gas phase primarily kind of migrates laterally and doesn't sort of come up back to the surface. And there is just a lot of this volume in general, and also like a surprising amount of volume available where you have both the good rock for kind of the flow of CO2 and also seal on top of it. There is just a lot of space.
Yeah. Okay. So this is interesting. Like probably the picture for many people might be, let's just find like a big cave or something and put it in there. But what we're saying is we're actually going to find, it's kind of like porous, so it's kind of like sponge-like, but it's rocky. So it's just rock with lots of holes, kind of, and there's water in there. We're going to inject this compressed CO2. So it's in quite an interesting phase when it's compressed, so it's like supercritical, right? So it's neither quite it's beyond the point where the distinction between liquid and gas makes sense. It behaves in some way like a liquid, and in some ways like a gas. We've compressed it that much, and then it goes into dissolves into the water that's kind of distributed through these rocks. And then on top of that, you're also looking for a place where there's like a nice impermeable layer, so it's not going to kind of bubble up. Cool. Okay. Yeah. Take us. Yeah. So you said that this is, I mean, standing back, if we didn't have geologists, and if we didn't have an oil and gas industry, it would be probably quite hard to find those sort of places, right? There doesn't, but I'm guessing that because we've invested so much over the last, century plus in finding underground deposits of things, like, do we have very good technologies for finding the appropriate places and getting to them?
Yeah, no, exactly. I mean, it is just like so similar in a way, to like exploration of oil and gas, is that I guess it is strange to me often that the idea seems so crazy to a lot of people because it is just literally the same, but instead of out, you're putting it in.
Yeah.
Like obviously, there's engineering challenges. It's a different phase. The methane, it has different buoyancy. There's different behavior, and so like there's the kind of like these engineering problems that people are addressing. But like it's not like a crazy idea. We're not like sending it to the moon. But yeah, we have explored the subsurface really well for oil and gas, and so there's seismic imaging of the subsurface. We can like predict really well where there's good seals, and for a lot of it also depleted gas fields where the hydrocarbons have already been extracted. You can use the same field to then inject the CO2 back in. So both the infrastructure, even the pipelines that we have, and
Mm.
also it's kind of understanding where to put it. Some of the wells can be like retrofitted as well. It's just
Mm.
very kind of useful for it. Also, like there are differences again in sort of how, say, methane behaves in the subsurface and CO2. But yeah, as you said, it's like CO2 acts as supercritical fluid at sort of subsurface temperatures and pressures. And that again like works out really in kind of storage favor, because when it's supercritical fluid, it becomes denser than water. So,
Mm-hmm.
and say like with natural gas, like the density of
Mm.
it is quite low. So we always have this kind of buoyant phase of, say, methane that sits above the water and sort of is trapped then by the seal. And yet still, we do have a lot of natural gas in the subsurface that has been there for millions of years until we drill these holes and taken it out. While with CO2, because it is denser, it starts kind of, sort of move, like it doesn't want to necessarily come up. It sort of starts, is even like convective sort of system with water where it sinks down and kind of circulates in the
Mm.
aquifer. So yeah, it is different, from hydrocarbons, but not in sort of really unexpected ways that is like a really sort of technical issue, I guess. Yeah, and I guess another kind of way. Oh, this is something that I've done my PhD on, is like, as I said, we have these natural analogs like natural gas fields, but also we do have natural CO2 fields. So already field like these subsurface fields in where CO2 is in a gas phase and is trapped there. And so normally, like the source of it is some sort of like mantle activity. So it's some kind of like volcanic source of it, right? We have some sort of volcanic intrusion in the subsurface, or maybe there's a fault where the mantle is then connected with our kind of more shallow subsurface, and so the CO2 gas is migrated from the depths and has been just trapped. And so there are these CO2 fields, and people have discovered them because obviously they're like looking for oil and gas, and then they drilled into a CO2 well, and it's like a really
That's
unhappy
disappointing.
discovery. But and then we can go and study these and sort of try and understand what happened. And we know that they have existed on the subsurface for millions of years, like associated
Mhm.
with, say, like volcanic activity that was active at the time. And so yeah, we have like I guess it's a really great sort of natural experiment on timescales that we can't really sort of replicate in the lab or various field studies, by injecting CO2
Mm.
and seeing what happens, where we can find evidence that the source of these gases, they have been sourced many million years ago, and they still are in the subsurface. So yeah, it
Mm.
sort of just really helps to build a lot of confidence that this is something that we can do.
Yeah, I guess that makes sense because we know hydrocarbons like stay under the ground generally unless we kind of pull them up. But yeah, there must be the worry that putting CO2 underground, maybe despite all of our beliefs, could it just kind of bubble up, or but you're saying, okay, well, no, there are lots of cases where CO2 is produced naturally underground, and we come across it, and we have it. We know that it must have been there for some time, I guess.
Yeah.
Yeah, and that's also super interesting, so that we can basically kind of use some of the existing wells and things and just run them in reverse almost. Does that work for? Is that a kind of special case, or are there a lot of places where that could work?
Well, it's more the pipelines of the pipeline can be used essentially. So depending how you transport the CO2, whether
Hmm.
it's in liquid or gas phase. So it's like pressure differences. But yeah, like a lot of the oil and gas pipe infrastructure can be reused for CO2. And yeah, in terms of wells, often I guess like I suppose like the easiest way to the easiest way to store CO2 would be into saline aquifers. Definitely, I think it would be something that just because where there isn't already hydrocarbons, so it would be great to drill new wells. But yeah, also like there people have used existing oil and gas wells for injection and things like that. So yeah, a lot of it can be reused. The main, I think, in terms of infrastructure and sort of financing all of this and making all of this happen, I think the main challenge is that again we're like talking about some kind of infrastructure that's really large scale, and there's like a few different expensive like tech that it needs to kind of all happen at the same time and
Yeah.
then be connected and then all be like economically viable for like a long time. So you need like some kind of capture plant where you're gonna commit
Yeah.
essentially. Then sometimes the problem is like, are we gonna have enough CO2? If we have the pipeline and we start injecting it, but like where is the source of it going to be? So is there going to be like enough plants that are capturing it and
Yeah.
sending it to the storage facility at a rate that's sort of needed, sustainable rate for decades? So essentially all of that needs to evolve at the same time. You need like all the capture plants, the
Yeah.
pipeline infrastructure for transport, and the whole storage and the monitoring. And so I think that has proven like really difficult to develop everything at the same time, especially when it sort of relies on industry to do it and have some kind of like financial incentives and security about their business models. Yeah.
Yeah, I think that it's a really good point. Again, it's sort of a point of divergence. One of the things I think that's just been, again, that's made solar in particular, but also wind just works so well is, I can have a solar panel on my roof, but it also makes sense to put a solar panel on like, an Amazon depot. It makes sense to build like 1,000, hectare solar farm. Like it just works on so many scales. So it's kind of easy to get going, as it were. Whereas, yeah, these big kind of carbon sequestration projects are big, right? You're drilling, I don't know, hundreds of meters underground. You need, lots of pipeline. That infrastructure can be reused at least, but these are $100 million plus projects to go, for a single one to get going. So I think we've got something like, I don't know, of order 50 that are operational, and they're pulling out of order, well, less than I think, is it like, I think less than 100 million tons of carbon dioxide a year, where we're putting in, 37 or so billion tons a year from other sources. So
Yeah, yeah,
still
yeah.
relatively small, and there's more in the pipeline, but it's, yeah, like you said, I think it's just hard to, this is not something that's going to bubble up in terms of just like lots of people deciding they're going to do it and like small financing and things. Like it's something where there needs to be kind of top down mandates and really big incentives for big investments.
Yeah, for sure. Like it needs some sort of like a regulatory framework, and essentially, yeah, it has to be like a government type of policy and project that we're gonna somehow incentivize this, and this is also going to be sustainable in terms of whatever legislation for decades, so that and so I think that part has been like very difficult to kind of coordinate. And because even the opinion of various governments has just been very different whenever the government changes of whether we want to support this technology or we don't. And as you say, it's like way easier to support something like renewables that is sort of like very, yeah, you can like the scale of it works on a small scale and a large scale. Well, this is something that's only going to work on a large scale. But yeah, there's like essentially right now there's this project called the Northern Lights project in the North Sea that's kind of run in Norway, where it seems like it's starting to have that infrastructure where there's like different companies as well as like the state of the government of Norway are creating the infrastructure, and it's like a business model where different industries can sell their CO2 for storage. And because there is like a carbon tax in Norway, it's sort of like it's creating now a system where it would work, where you could have like enough CO2 because there's many users that might want to sell it, and they're incentivized sell it, and then it is a kind of like a business model for the storage, part of the chain to kind of earn money from it, I guess. So yeah, something like that, I guess, is kind of how this would work in practice. Yeah. But yeah, I guess
Okay,
like
yeah.
the main point I have is that there is just like no shortage of space underground for storage, but like making it all work in terms of like economy and industry and like these chains, interconnected chains of industry, is like has been the difficult part for sure.
Yeah, I think that's the key message, right? That we know how to do this. We're doing this. We can do it at even greater scale, in terms of engineering requirements, but it's just getting the financing in place. So people shouldn't say, "Oh, carbon capture, that's a moonshot," right? Maybe it's an economic moonshot, but it's like something the technology is absolutely down.
Yeah, but also like I mean, it is a good, I guess, like evolution of the concept, because again, like as I've said, in the early days, there's been this concept of like, okay, well, we're just gonna continue burning fossil fuels and build this whole huge industry to sequester the CO2, and it has been questioned whether this is like the most efficient thing to do, really. And so if you keep kind of developing like what exactly is the model of this and what's like the optimal way of doing it that does make sense, I think eventually you can, you get to a point where it becomes something that makes sense in the whole society, kind of in the economy. So I think it's made in that way. Yeah.
Cool. All right, I think let's talk about something else, which is also related to geology and climate change, but probably less known. And so hydrogen. There's a lot of excitement, or there's been a lot of excitement around hydrogen for many years, and kind of talk about a hydrogen economy. And we can talk about how that economy would work. But I think one thing that mostly people have agreed on is that the way that we'd run that is by, the optimal way of doing that would be electrolyzing water, creating hydrogen using abundant renewable energy, which is becoming cheaper and cheaper, to make that model work. There's obviously other ways, and people will be familiar with, you can get hydrogen from methane. That's not really that great, but there's lots of other ways of creating hydrogen. But sort of the hopes, I guess, have been set on this kind of electrolysis model. But that requires a lot of energy, which you could be using to actually you could be putting that into the electricity grid to do other things. It requires a lot of electrolyzers, which are, expensive to build and, not completely efficient, maybe 70% efficient as well. But there's another thing on the scene, which people won't know about, which is hydrogen from the ground. So firstly, does this, I was reading on the kind of National Renewable Energy Laboratory website of the US, it says hydrogen does not typically exist. It used to say, in fact, hydrogen does not freely exist in nature at all. Just a couple of months ago, it said that. So there is this kind of this long been a belief that hydrogen just doesn't exist as, H2 as a molecule on its own naturally. But I think you're going to say that that's not the case. So yeah, please kind of tell us, is there hydrogen out there? Is there hydrogen in the crust naturally?
Yeah, so yeah, I think it is a really sort of exciting now field of research of looking, as you say, for natural hydrogen that occurs just like oil and gas or CO2 that we naturally see in the subsurface in this like molecular form as H2. And it's a fairly new idea, and people haven't really thought about exploring for it before. And to some degree, I guess like there, people didn't maybe think it exists at all. But for most part, even people who thought that it exists, like didn't quite think that it would exist in kind of places and quantities where it make any sense for us to try and like use it, as a resource. And we start really finding a lot of evidence to think otherwise right now. So it is becoming this like really interesting kind of research area and exploration area already. So compared, to other ways of making hydrogen, like I guess the majority of hydrogen that we use now, and there is a lot of demand for hydrogen. It is like a multi-billion dollar industry, even without sort of using hydrogen in various kind of ways that we see in the future, and we can debate about, how we might use it in the future, whether it's gonna be used as for transport or not, obviously. But like right now, we use it for various, again, just industrial processes, and primarily like making fertilizers, so making ammonia for fertilizing. And so yeah,
So
there's a
ammonia
few of
is
these.
like so ammonia, I guess, is just like nitrogen mixed with hydrogen, basically, and
Yes,
we
yeah,
get the
nitrogen
nitrogen
mixed with
out of the air,
hydrogen.
and we get the
Yeah.
hydrogen in different ways. Yeah.
Yeah, and so right now we get the nitrogen from the air, and we get the hydrogen from hydrocarbons. So yeah, we kind of remove the hydrogen from hydrocarbons through like steam methane reforming, and again CO2 is vented. The hydrogen we use for something that we need the hydrogen for, and again that constitutes already, like without any sort of like thinking about future hydrogen economies or something like that, to about 2% of global emissions.
Mm.
So if we can do something about that and not use this hydrogen from hydrocarbons, that would be excellent. And it could be using green hydrogen. But yeah, as you said, this again, like producing hydrogen in mass scale using electricity lives again in the same world as various other technologies, of where we have just really sort of vast amounts of cheap renewable energy.
Yeah.
But yeah, right now that is expensive, and so the cost of that is predicted to fall in the future. But if we could just get hydrogen from the ground that is not associated with carbon at all,
Mm.
and the production of that would be way cheaper, that would be excellent. That would be a great way to solve this kind of 2% of global emission problems to start with. And however the hydrogen economy would evolve in the future, we could see where that fits in the place. But yeah, so the idea of this geological hydrogen, and like where does it come from and why did we never know
Mm.
about this, I think is quite
Yeah.
an interesting question. Yeah, so I can talk about how it is produced in the earth, and yeah, maybe I'll touch a little bit about kind of how we also like learned about it in kind of
Mhm.
academia, because yeah, my focus and sort of work with it has been from this more academic perspective that didn't really have anything to do with resources. And so yeah, it's kind of been a new idea that we can maybe actually explore it for the society. But yeah, so there's like two main ways of how it's produced. And so one of the ways is water rock reactions. So it's a sort of reaction where water reacts with this kind of volcanic rock, a type of rock that is really iron rich, these sort of ultramafic rocks.
Mhm.
And they'll produce this mineral called serpentine, and hydrogen is a byproduct of that. And so
Mm.
we have known about these reactions for a long time, but so they will happen in various places where these kind of mantle rocks can be it sort of interact with water, so potentially like mid-ocean spreading ridges where you have kind of like deep mantle rocks and water sort of circulating, or subduction zones and things like that. So yeah, this
It's
process.
basically oxidation, right? It's like rusting of the rocks, and so
Yes, essentially, yeah.
basically, yeah, the oxygen gets stripped off the hydrogen and makes the rocks kind of rusty. Although you'd think that would make them red, but I guess it makes them green because
Yeah.
creates this serpentinite thing. But anyway, it's kind of rusting, I suppose, to sort of make it more prosaic.
Yeah,
But
yeah.
yeah, so come on.
So yeah, so and kind of the importance of the production of hydrogen in this process like has first been discovered in the 1970s, where people have predicted that there should be these sort of things at the bottom of the ocean, these kind of vents where we have the kind of hydrothermal fluids coming out of the seabed. And then in the 70s, for the first time on some kind of cruise, they observed these, and they are these like really interesting features generally, because they kind of if we're thinking about like the ecosystems at the bottom of the ocean, like the deeper you go, the kind of the less life there is. It's more energy
Mm.
constrained. So we have these sort of really energy constrained environments where there's not a lot of biodiversity and things like move very slowly. And yeah, these hydrothermal vents that I think like many people will have seen in various nature documentaries or photos of are these kind of these sort of black chimneys, kind of these smoking chimneys at the bottom of the sea that are associated with fluids coming from depths that are rich in various like metals and all kinds of bioavailable molecules. And they are these really fascinating ecosystems. And because what happens is essentially what you need is some kind of source of heat, which will, in the case of these vents, is to do with kind of the heat from the mantle and the spreading of the ocean floor. And so you have this heat that kind of creates this kind of circulating system in the fluids and the rocks. Again, as I've said, all the rocks are at the bottom of the sea and below the sea are saturated with water. And so you start circulating this really hot fluid, and it starts then leaching like minerals and elements out of the rocks. And there's all kinds of reactions happening, and it's a sort of like hot pot of creating things. And so around these then like events, you have these really kind of interesting, diverse ecosystems where like in this kind of sort of desert type of almost environment, but submarine, suddenly have these like live hotspots. And so people have started studying them and found this kind of really fascinating thing that there are microbial organisms that use hydrogen as their primary energy source. So, and essentially, it has been like this discovery of this kind of second type of life, if you will, because like our understanding of life has always been that we have the primary production of energy from photosynthesis, and this is the plants and algae. And that's kind of the very base of kind of the chain of the food
and obviously
chain, and
that uses and
Sorry.
obviously that uses oxygen, right? Like
yeah,
and not hydrogen. So it's kind of surprising to find that we've got these microbes. And was this like just a discovery back then that there were these other kinds of microbes that were using hydrogen?
So it has been just a huge discovery, because we're like, okay, well, we're there's like the energy from the sun, and and it's combined with CO2, and you can make these like organic hydrocarbons, and then actually we have, and so the further you are from the sun, the more difficult it is for life to have energy. And then suddenly, like, it's kind of this alternative to the sun, we have hydrogen. You can combine it with, say, sulfate. You can essentially like remove that electron from hydrogen and use it as energy to kind of produce food, if you will, for microbes. So there are then all these microbial, and it's called chemosynthetic life rather than photosynthetic life, because it uses this chemical energy from the earth. And that was like fascinating, because it's sort of like we had this understanding of how life exists and kind of the ecosystem chain. It's like, oh, okay, there's like a different ecosystem now that has different energy source, and kind of opened a lot of questions of well, what do we think about then? Like, what's the impact on origin of life? Like, could life have originated in these sort of places? Or also, like, how does it work if we think about other planets? Could we have systems like that? Where, say, in Mars, not so much the vents, but generally, if you're thinking about the subsurface, if we can't have life on the surface, maybe like deep in the earth, you can have like hydrogen, dependent life. So yes, and so the hydrogen question has become really important, because that if that is a fuel for life, that it's sort of like, well, it's interesting to then quantify it and understand like what are the production rates of all of this. And so the vents, I guess, like has been cool. And then I think only in like something like 2013, people also in the community of sort of it's like oceanography and stuff have discovered that actually it's not only around the vents, but if you go on the subsurface, there's all of these microbial communities living in the pore spaces there in rocks, still eating hydrogen, and like have their whole ecosystem going on. And so that kind of really, like, again, like expanded our understanding of what's like inhabited, I guess, on the planet. So it turns out then there's a lot of the subsurface also is a biosphere, and it's powered by hydrogen. So this, water rock reaction, hydrogen, then has been kind of like studied a lot in the kind of communities, mostly to do with trying to understand biology, trying to understand the kind of significance of origin of life, and like astrobiology, like in particular, like really trying to understand like whether these kind of systems could exist on other planets and what we could expect in there. So like, I mean, a lot of people have known about it, since the 70s, but again, we're talking about producing hydrogen in some kind of sea vent, or like in pore spaces. So it doesn't necessarily sound like this is something that we could like tap into and use. All right. um,
Yeah,
yeah, and
this
so
is.
that's yeah.
So I was just going to say, it is like I know it's like I don't want to go on too much of a tangent, but it is so interesting that there is this kind of yeah other energy source for life, because I think everything on the surface, right? We all get our food from the sun one way or another, right? It's all, whether you're a lion, right? You can
Yeah.
trace that food chain back. It gets down to plants, and they're getting their energy from the sun. But yeah, so I feel like there's like a great sci-fi novel to be written here about, you know, beings who are living underneath the earth, never seen the sun, but getting all their energy from chemosynthesis. Yeah, that's just so interesting. But yeah, as you say, yeah, it doesn't so far, like, okay, so I guess we know from these ocean, we know from that there's microbes that are living off hydrogen. We can see this hydrogen. We know it's present from these vents, but kind of, yeah, doesn't necessarily seem to solve our problems of using hydrogen in industry and fertilizer creation and so on, because not easy, like not easy to
Yeah,
get
well,
down to those vents and like,
need to steal it, from the microbes, because
yeah, they're not going to be too
these
heavy.
ecosystems thrive because the hydrogen available is definitely a lot of spare that going around is consumed in this energy
Right,
constrained
exactly. So they're
environment.
eating this, right?
Yeah,
They're having our lunch.
yeah. Yeah, but so yeah, at sort of around the same time also, so this is kind of like talking about the oceans, and then at the sort of same time there's this research going on in the subsurface of the continents, and kind of what's going on in, as I've been talking about this water that is in the subsurface, and the question also has been of like just how far the water goes, and like how like sort of, because as you keep going down with depth, I guess these pore spaces and fractures and rocks, they keep getting, because of pressure, like sort of, they keep getting smaller. And like, can you like have water in there, and is it actually circulating if you have it? And so we've had these observations, and it's also like subsurface is like such a kind of relatively like underexplored, I guess, territory, because it's just so hard to get samples from very deep, right? Like it's very hard to access directly. But like some of these really interesting observations have come from really deep mines. So for instance, in South Africa and Canada, like some of the deepest mines in the world are up to like down to four kilometers at depth. And so uh, and then in these places, when people mine, often they'll hit some kind of fracture, and that fracture will flow water, and there's like, turns out there's like a lot of water in these fractures. You can hit one, and you kind of just tap this like underground hydrological system, and it will keep flowing for like a decade, and it's kind of an issue.
Okay.
It's an issue, but also like a really interesting thing is like, what is this water, and where like where does it come from? So people have collected samples of these waters in the deep mines, and have found, again, surprisingly, that it like is full of this chemosynthetic life, that is also again like getting hydrogen from something. And yeah, I think especially puzzling, these observations have been in places where we don't have these kind of igneous rocks, like these iron-rich rocks where we can produce hydrogen in by reacting with water. And so the question is like, how is that now living here, at these depths? And so the second way then, like that, yeah, brings me to that kind of second source of hydrogen, of geological hydrogen, is radiolytic hydrogen.
Mm-hmm.
So it is produced essentially by radioactive decay of radioelements. And so there are radioelements such as uranium, thorium, potassium, that are kind of in trace amounts in rocks kind of everywhere. And it's quite like homogeneously distributed. So it sort of, yeah, we have like a similar amount of uranium just about everywhere, except maybe some places where it's enriched. And so these radioelements decay kind of very slowly. And as they decay, they sort of emit this, they emit this ionizing radiation. And if there's like a water molecule in the vicinity, that can split the water molecule, it can produce all kinds of compounds, like including hydrogen. So again, this like the kind of the production of hydrogen through radiolysis wasn't like in terms of physics and everything, was kind of a new concept. But then the idea that you could just with trace amounts of these radioelements, you could produce it at some kind of rate where it could sustain an ecosystem, especially an ecosystem in the subsurface that is like entirely separated again from photosynthesis and somehow lives there for millions of years, has been like really new. And so people haven't quite considered of how much hydrogen can we actually produce, like where is this water, how much of it there is, like is it close to these radio elements. And so after discovering these life forms, you kind of have to explain of like how do they live there. And so people then have like done an assessment of sort of the radiolytic hydrogen, and turns out again that there's actually like a lot of it is being produced. We have a lot of water in the subsurface, and it is being produced slowly, but at a rate that is good enough, essentially, for these microbial ecosystems to kind of live entirely independent life to, photosynthetic life. And again, the subsurface is full of this chemosynthetic life. So there are the two sources. So we have it all, under the sea, and we have it in the subsurface and the continents. And it's primarily just been studied, and like I have studied it in this kind of context where I just find it fascinating that life somehow lives on this, and the question is how. And especially in the continents, the production is very slow, and so some of these forms of life are really fascinating. In that they have like these really slow metabolisms. They sort of like divide a cell like once in 1,000 years, and they have these lifespans that are like really long. And there's the kind of like it's still an open question of like how long do they live. And some people seem to think that they can like live on kind of geological timescales, whereas somehow part of their evolution strategy is to kind of move with plates and go through different environments. So I mean, that's a tangent. But anyway, that is kind of like, I guess, where the research has been. And so like how, I guess, what brings us to then thinking about this as a resource is that in some of these places where we have samples from the deep subsurface, we also have found where there is just hydrogen in the molecular form. We do have fractures somewhere in various places where hydrogen exists, and none of this life that is so energy constrained has managed to consume it. So that's interesting. That's interesting then in terms of like finding places where something else is essentially inhibiting the microbes, and maybe they can't consume it. And so essentially, like the hydrogen that's produced on the Earth, I think for the most part, it is part of this ecosystem. It's produced, it's consumed at the same rate. There's an ecosystem around it, and then there are special cases, like in the same way as with everything, like with oil and gas or anything. With oil and gas is like most of you'll produce gas from these organic compounds, and it will just diffuse through water and escape somewhere. But if you have a seal, then you might capture it, and that's a special case where you can drill. And so the same is true for hydrogen. Like for the most part, it's consumed by microbes, and in some places it isn't. And like I guess when all of like as we've kind of learned more and more about hydrogen, people have kind of looked back at the literature record of observations, and turns out that we have like very many observations actually of hydrogen in molecular form, like occurring in, say, again by accident found in gas fields where it's kind of mixed with hydrocarbons, and people just didn't think much of it. Or there are hydrogen seeps on the surface. For instance, in Turkey, you can like find hydrogen seeps. And so there are actually very many observations around the world. And for the most part, people didn't really think much about it and attributed the source to something like kind of way lower scale, and something that doesn't, quite imply that this could be a resource. And so there's been this kind of big reassessment of what we have observed around the world. And we have observed that in a lot of places it can actually be preserved and not consumed by microbes. And so that's kind of where we are now. Sort of, we have learned a lot about how it's produced and how it's consumed, and we're really starting to find places where it isn't. And doing research into finding places where it can be not just like not consumed, but also stored and sort of concentrated and stored in some kind of way where we could easily drill and sort of just explore it.
Because as you say, like if it just seeps out and it may not be consumed by microbes, but if it kind of just seeps out in really kind of low quantities, and it's no good. But it is super interesting that despite all these signs, it kind of wasn't. As I mentioned, like there's various sources which say, either just flatly that hydrogen doesn't exist, like on its own in natural form, or that it's typically not on its own, which is like a very fair. That's probably true. I mean, there's a load of water on the planet, right? So to say that the typical form of hydrogen is combined with oxygen, I think, is a fairly safe but bland statement. But so it is fascinating that it wasn't observed more. I think one of the things that struck me was that just no one was looking for it. And in fact, the kind of chromatography techniques that are used, so this way of determining what gases or chemicals are present in a substance, used hydrogen as a medium, if I understand correctly. So it was like, which meant essentially that it was kind of like the substance that was used to kind of dissolve all the other gases in. So of course you'd expect to see hydrogen, right? But it's not. You kind of designed those equipment searching for, seeing what you had in terms of methane coming out of a vent or something. It was designed to look for everything else apart from hydrogen.
Well, yeah.
And no one was really. I guess no one was interested in looking for it. There is a story, you must know this, about Mendeleev, who reported that he'd found hydrogen or in a kind of mine in Ukraine or something. So originator of the periodic table knew about this. So it's like it shouldn't be news.
Yeah. Well, so there's way more kind of observations of natural occurrence of it. So as you say, like it's kind of like our kind of understanding, especially of subsurface, because it's so hard. It's so hard to mass observe things. Like say various things at the surface. Now we can use satellites, and we can like collect a lot of data, and then we can think about later what we want to get from this data, and potentially we can find things way in the future about what we've already collected. But like with the subsurface, it's always like so intentional. You're going to go look for something and you're going to measure something relevant to what you're looking for. And for the most part, it's been oil and gas. People have been trying to find hydrocarbons. So it's really haven't been collecting data on hydrogen. And even like in terms of the measurements that exist, like often from the oil industry, the kind of data sets are quite unreliable. Like also, it's not really incentivized that you need to have like really great precision on some of these measurements. It's just if you found some methane, that's great. You can run these other measurements. It doesn't matter if they're wrong. And so like a lot of what's reported is kind of like, questionable quality. But there are like way more observations of hydrogen in a kind of the sort of, I guess, geographical area of like the former USSR. Because there was a theory there of Russian scientists where they had a theory that hydrocarbons are produced inorganically somehow, and there's like hydrogen involved in this, and it's produced like by reaction of hydrogen and CO2. So it's way more documented there, and because they've been looking for it, and so now that we have like a hydrogen kind of, well, we've have these maps of where hydrogen has been observed, it seems like it's just been like in Europe somewhere, and it is because like where people have been looking for it. So it's kind of interesting observation bias, and the same is true for like finding it in a subsurface. So there have been accidental discoveries with oil and gas, or like an interesting example, which is actually our first and only so far commercial hydrogen field in Mali in Africa. Where there is like an active, hydrogen, there is like 99% hydrogen discovered in the subsurface at the depth of 100 meters, which is like quite different, for where you would look for something. And people have just drilled a borehole looking for groundwater, it's a groundwater borehole, and have like struck hydrogen unexpectedly. And also, I think that the account of it is sort of, we drilled a borehole and there was wind coming out of it and it was confusing. And then somebody, like, unfortunately, like, lit a cigarette and had like, suffered a serious injury from it. And then I think they shut in the borehole, and only like some years after, and the company came in and started developing it. So where it does occur, it tends to be different places to where oil and gas occurs. So therefore, even though we drilled so many wells for oil and gas, only in some instances we found hydrogen, because for the most part, from what we know about how it's produced, we expect it to be somewhere else. So that's again another reason we're not measuring for it, and also we're kind of looking for things where it probably isn't, is why we haven't seen very much of it.
Yeah, and it's like odorless, colorless, very very low density, so it's kind of hard to see, right?
Yeah.
I want to talk about, just before we get on to sort of like the nuts and bolts of how how much we could extract and where we might look for it. One other like really curious thing I came across was, as kind of evidence that there's hydrogen, is these kind of fairy rings, which go by different names. They also get called Carolina bays in the States, and I don't know, fairy circles and so forth. So maybe just tell us about those, because this was like another, there's so many like tiny like tidbits, like mini mind-blowing nuggets in the search for hydrogen, and this was one of them. So yeah, tell us about fairy rings.
Yeah, so I mean, fairy rings are these kind of circular depressions on the surface, and you can see them from satellites, essentially. And I think the kind of the really big incentive to like really focus on fairy rings was because the Mali discovery was associated with a fairy ring. There's a fairy ring there, and there's hydrogen seeping at the surface. So there's observation of this formation, and essentially what it is, it's something that can form where you have deep fluids that, through some kind of fault and fracture system, are coming to the surface. And so that they will form this kind of circular depression and emanate from the surface. And so the Mali discovery, is associated with fairy ring that is associated with actual hydrogen observations at the surface. And so then people start looking for them, as indicators for hydrogen. And I guess like the usefulness of that is, I think still, to really kind of be be proven, because really like quite a lot of them exist around the world, and it's not something that you expect only if hydrogen is part of the fluid that migrates. It's actually something that you can't expect forming at the surface if some kind of deep saline brine is migrating through the fracture network. And so like we are expecting to see hydrogen in these deep saline brines. That's like we're associating with these deep saline brines in the subsurface, and if they are mobilized to the surface. But also you can just have a migration of this brine without the hydrogen and still form a fairy ring. So it is not necessarily kind of an indicator, yeah.
Okay, so the fairy rings are probably more associated with or caused by these kind of saline brines, which I guess kind of dissolve some of the minerals below them, and that's why you get this depression. I think there's also like a kind of like change in the vegetation as well, which presumably is like associated with the salinity. But yeah, I guess fairy rings are sort of like a sign that there might be hydrogen, but it might just be saline, like brine on its own.
Yeah, exactly. And so also, then people have detected hydrogen at sort of the soil gas in Mali, and so there've been a lot of efforts of measuring hydrogen in various other fairy rings, and for the most, like, I guess, if you're going to go around and measure all of it, I think it can provide a lot of clarity. But often, people do measure trace amounts of hydrogen, which can actually come from these like very shallow kind of biogenic sources, like again, just sort of microbial surface processes. So you can have a fairy ring and then measure also some hydrogen. And then again, that like will not indicate that it necessarily is coming from depth, that might indicate something quite shallow. So yeah, like the evidence for kind of necessarily using fairy rings for exploration is like a little bit mixed. But yeah, it is a feature that can be but isn't. Yeah, yeah. Yeah.
So how do we? So where do you go looking? Right. What are the promising places for?
Yeah, so the places are again, these kind of places where we can expect these water rock reactions or radiolytic production of hydrogen. And so there are like really like very many places in the world where there's some of these ingredients are there. And yeah, the question is like to find a place with all of the ingredients, with the production and with like a trap and seal and some kind of system where also the microbes have been prevented from, having their lunch. So like one of the type of places is looking at cratons. So cratons are these kind of on continental crust, or these areas where essentially it's some of the like oldest rocks on Earth, where we have these rocks that have been part of continental crust for billions of years, and they have been tectonically like fairly stable. And so these are sort of examples that are similar to these observations that we had of both hydrogen and fractures and also microbial life in, say, South Africa or Canada. And they're like really, there's a lot of, different cratons on sort of on every continent. So what would be very good for production of radiolytic hydrogen is having this kind of tectonic environment where you have deep fluids and these rocks that are sort of stable for a very long time. And also because the radiolysis is a slow process, that you would be able to accumulate this hydrogen for a very long time and then kind of not lose it by sort of tectonic activity and fracturing and things like that. So yeah, like one type of place is looking for really old, kind of ancient, very stable continental crust, where we had time to accumulate it for long periods of time. And then perhaps ideally combined with maybe like some tectonic activity, not too much, has some amount of tectonic activity at some point, perhaps not too long ago, where it would mobilize then these fluids it kind of to some formation above it. But there are very different kind of ways of thinking about also like the reservoir rock for hydrogen, because we can think about it in a more kind of similar way to oil and gas, where these cratons are source rocks, and then we need to mobilize into some kind of porous sandstone with like a seal on top. But at the same time, it is also possible to think about like fractured kind of basement rock as the reservoir. So one kind of exploration strategy is looking for really like old stable tectonic crust, and then secondly is the water rock reactions. So finding areas where you have these ultramafic rocks and water. And so then the advantage of these systems is that the reactions can be way faster. So you potentially don't have to wait 2 billion years for generating your hydrogen. And also like what's kind of in your favor is then if you are producing it this quickly, then potentially, there's too much of it, the kind of ecosystems are going to then be limited by something else than hydrogen. It might be too much hydrogen, but you're limited by, say, CO2 or something. And so then the microbes can't like keep up with the consumption. And so like both the kind of they tend to be in quite different places in the world where you have these type of kind of igneous rocks and the old cratonic crust. But in terms of the reaction rates of the water rock reactions, we know that it's faster. It's faster than radiolysis, but also like the range kind of like how fast these reactions can happen is kind of not very well sort of understood. Like it can range from very slow to very fast. And we don't quite have enough research of sort of really quantifying it and especially quantifying the important factors of like what makes it very fast and what makes it very slow. So yeah, again, this is like the sort of a field of research that is really happening.
But I mean, it is so it is really unusual to think that this could be kind of almost like a renewable, like if so the radiolysis is one thing that's super slow, that's in the cratons, but the kind of serpentinization route for creating hydrogen, where you've got the water reacting with kind of iron and minerals, that keeps on going. So you could have a mine, and as you say, we don't know how fast it is and what makes it fast or what makes it slow quite yet, but you could have a mine which just kind of keeps on refilling itself in principle, as long as the water keeps coming along and there's still enough minerals there. But there's kind of no reason to think that just can keep producing hydrogen, I guess.
Yeah, I think, well, that's been a proposed theory for the Mali discovery, because they have been producing it now for like about a decade, I think, and they've not observed any pressure drop. So it seems like, they keep extracting hydrogen, and more of it is coming up. So yeah, one of the proposals is that it's because it's actually like renewing in kind of real time.
Mm-hmm.
I think I'm not quite in favor of that. Like, there is definitely like a lot of uncertainty in terms of the reaction rates, but I think
Mm-hmm.
there's maybe like not quite the evidence to suggest that they're going to be that fast, like it's sort of
Mm-hmm.
human timescales. And because like, I suppose like the main kind of limitation in terms of kinetics is like the reaction can happen quickly. Yeah, if you have these sort of iron-rich rocks and you expose it to water, it will probably happen very quickly. But then it will like react out, and it will stop, and kind of what makes the reaction happen again. And so usually I think it is something to do with creating new surface area, like fracturing that rock a bit more, so you have
Mm-hmm.
water like percolating a bit deeper, and so it can continue reacting. And so like I don't think this necessarily happens at human timescales. But I think potentially what might be happening is that there is like a reservoir of this gas that it is actually filling these other more shallow reservoirs. And so the more you extract from more shallow reservoir, like more comes from the deeper reservoir or something like that. So potentially just like what they're tapping into is probably just way bigger maybe than is kind of thought right now. But yeah, like I think like it's definitely really interesting in terms of serpentinization, that the reaction can happen fast. I think we're not quite at a place where it might just sort of keep going if we keep extracting it.
Mm-hmm.
But then there is also this kind of interesting proposal of again yet another color of hydrogen called orange hydrogen, where it would be like an industrial process where you would find these rocks that would produce serpentine, and inject yourself, like fluid, water with CO2 as well, actually. So it's like a
Mm-hmm.
combined, you produce hydrogen and sequester CO2 at the same time. And
And I
in
guess the
this kind of
CO2
situation,
stopped your
yeah.
microbes from. Probably the microbes don't like the CO2 too much. Is that one of the reasons to do that as well?
Well, it is just a sort of because then, like, if you just produce hydrogen, you produce a serpentine mineral. But also, then if you add CO2, then the serpentine mineral can react with the CO2, and you can then like form carbonate minerals. So yeah, the main kind of incentive for this is to combine both like sequestration and
Okay,
production of hydrogen. But yeah,
we're bringing it
I
all
guess like
together.
yeah,
This is
yeah,
great.
yeah, it's great. Like, I mean, I do like orange hydrogen, but yeah, in this case where like if it is like some kind of more engineered process, and we are controlling, well, maybe like we keep fracturing this rock, right, and keep
Mm-hmm.
opening new spaces by injecting, it is, I think, something that can it can then be renewable.
Mm-hmm.
But yeah, it is something to really be shown. But yeah, I think it is also really promising in this, especially this kind of combined effect. Yeah.
It, maybe I mean fracking's got a bit of a bad reputation, but is it a kind of similar process to fracking? But instead of taking carbon and putting it into the air, you're actually putting it underground, and instead of getting methane out, you're getting hydrogen, which again is not going to put
Yeah.
not going to put any
Yeah, I
carbon
mean,
in it.
it would essentially be a similar process. Yeah, so it is induced kind of fracturing of the subsurface, and yeah, the risks and all kinds of things associated with it are, similar. That obviously you want to create some fractures. You don't want to create too many. You want to
Mm-hmm.
predict where that happens. You don't want to create any earthquakes. So yeah, the implementation of all of this, um, and yeah, like what kind of depths you're going to be operating in, because there is like a temperature window where these reactions happen. Yeah, like all of that is associated with the same kind of risks, and having to mitigate them as fracking. Yeah. Well, I think
Yeah,
like,
yeah,
maybe
yeah.
the kind of better part of it is if because it is essentially like the kind of rock is quite different, and so if you end up like having sort of unintended fracturing and fluid movement, well, at least it's like not methane that's coming up to your drinking water.
Yeah, yeah, yeah. I think that's an important point. I mean, there's kind of risks with many things. It's just with fracking at the moment, there doesn't seem to be much reward, right? You get methane, which is like, you can sell that, but certainly not great for the atmosphere. So yeah,
Yeah, I mean, it's just
I
a
think
way,
like
a
we need to.
efficient way of extracting. Yeah, I mean, it's really bad. I think certainly there's like something that's really underestimated is because you create all these new fractures, then you kind of really increase the rate of just diffuse leakage. Like, you
Mm,
don't necessarily have leaks where there's like like gas is just bubbling up through a big fault, but you're really increasing diffuse leakage just everywhere, kind of to the surface, to the point where it's not really monitored. And I think, yeah, it does really, again, just contribute to these kind of like slow background emissions to the atmosphere, like a huge amount.
yeah, yeah. I think we'll probably need a new label for orange hydrogen production. We can just call it orange hydrogen production and move away from the fracking history as as you say, it's different rocks in any case. But yeah, that's so. I mean, yeah, we now have different places to look. There's kind of the cratons. There's the places where we think serpentinization can be happening. We have at least one example of that in Mali. So this is not sci-fi, right? There is hydrogen there. It's
Mm-hmm.
actually being used, as you say. This is a kind of commercial operation that's running there. And then we think we could, I guess, if we were to produce orange hydrogen, would that open up a lot the kinds of places that this could work, or would it sort of be more where the serpentinization you can speed that up? Yeah, how does that look?
Yeah, for sure. Again, that's just, targeting, like, that's just really targeting the type of geology, and seeing where it could work. And like, I guess even like what I think could be an exciting avenue for this, if say like if you are drilling and exploring for you're hoping that there's going to be this natural hydrogen produced by natural serpentinization, and so you're kind of targeting these ultramafic rocks. And you drill, and perhaps like you don't find hydrogen, well, maybe you can then just make it, right? So it can
Mm-hmm,
be like a
mm-hmm.
combined thing. Well, if you didn't find it but the right geology is there and that's why you drilled, well, perhaps you can then inject water and kind of make it yourself with CO2, perhaps. Yeah. So yeah, I think these are kind of like interesting combinations of both, like maybe in terms of exploration strategy, how you can kind of combine and reduce risk of what the operation is going to be, and how you're going to utilize the like resources.
And are there a lot of? I mean, are there quite a lot of places where this could work? The sort of thing I'm thinking is one of the real. Let's think of it like this: like, so to sort of get hydrogen really off the ground, you need there's like the costs of in the kind of electrolysis world of hydrogen production, you've got the energy costs of electrolyzing stuff, you've got the capital expenditure associated with creating all those electrolyzers and also fuel cells as well. But let's just think about the production, and I think that counts for. I was reading in the FT, and you sent this article, so you're probably familiar with the figures.
Mm-hmm.
So the FT predicts that sort of about 3/4 of the cost of kind of building a hydrogen economy, which they kind of estimate a hydrogen economy would sort of cover about 10% of our energy would come from hydrogen, and so a lot of that would be, or some of that would be fertilizers, and then there'd be other things. But I guess the point is, yeah, it's kind of 3/4 or so of the cost of building that is associated with just producing hydrogen. But then there's another quarter which is associated with all the infrastructure that you need to work with hydrogen, because it doesn't go through our normal pipes without modification. Like, you have to compress it, you have to figure out how to move it around, and so on. So that's still like a really substantial chunk of money, and clearly, like the sort of geological hydrogen has the potential to really reduce that 3/4 cost, so the cost of producing it. But I'm also wondering, like, if this is something that could run in many different locations. Like, could you collate? Could you put it near like a cement plant, right? And then use it as your hydrogen source for that, or could you put it near like the fertilizer production sources again, or is it, will we still have to build a pretty substantial infrastructure for, say, moving hydrogen from Mali to Germany and things like that?
Yeah, no, like definitely in terms of like geology where it's possible, it is yeah, like there are many like potential locations on a planet where it could work. So there's a lot of different combinations of what you could combine with. So say, like these kind of Precambrian like rocks are older than say 500 million years that are often seen as sort of the good source rocks. They cover most of the continent. Something like 70% of the
Okay.
subsurface is sort of these sort of rocks. So there's a lot, right? And as well as these iron rich rocks. And then like the first estimate is there's a lot, and then you keep kind of sort of excluding places. So like where is it going to be trapped, where is it going to be not consumed, and then finally, like in terms of any exploration, like a really big factor, and especially starting any new kind of sort of project, is also finding a place where it would be close to some kind of like industry or some kind of infrastructure where, as you say, like is it close to where we produce fertilizers, because we don't want to transport it like halfway through the world and then it's going to become just like very expensive and not really worth it. But yeah, I think like the kind of variety of geological terrain that is suitable does definitely map out to like a lot of different options of what you can combine it with. And I guess another thing that I haven't sort of touched on is helium, which again is like is like super useful gas that we are exploring for. It's a noble gas, inert gas that's used a lot in kind of in high tech kind of industry. And again, the sources of it is in the subsurface, and it has been mostly found by accident and kind of trace amounts of hydrocarbons. But from what we know of how it is produced and so how hydrogen is produced, like the places where we expect to find hydrogen, we also expect to find actually high concentrations of helium. So there is this kind of also incentive of combined essentially. We're expecting to find both these gases, and if we can tap into markets where both of them can be shipped to somewhere close by, I think that really like makes it like a compelling economic model.
Yeah. And of course, where this, I mean, coming back to the kind of beginning of the discussion is, these are going to be CapEx high projects. Like we're going to have to invest a lot, but there is a very clear incentive to do so, right? Because if you can get out hydrogen, and even better, also you get some helium as well, that's. I think the interesting thing about helium is it's historically had a very low price because we've just like overmined it, but that price is probably going to go up as like our reserves have drawn down. So yeah, there's lots of reason for the sorts of kind of deploy those expensive technologies, which I guess we can repurpose from the oil and gas industry, right? We know how to drill big holes. We know how to search for things underground. Like there's lots of reason to bring that to this quest. And actually, instead of taking out carbon from the ground and putting it into the atmosphere, we take out something which is no carbon at all, just hydrogen. But yeah, nonetheless, great source of fuel. So yeah, that's super promising.
Well, I guess like one thing that I think is really exciting for me about hydrogen, natural hydrogen, is actually like it is in such a different kind of boat to CO2 storage, where like CO2 storage is this kind of thing we have to do, and it's big and is going to require a lot of investment, and we're going to see payback because it makes sense. We're going to have to do negative emissions at some point, and it makes sense, but it doesn't make sense in the kind of this very like fast economic kind of sort of way of thinking, where like when is it going to pay off? It's going to pay off when we don't die from the seals boiling. But in terms of the natural hydrogen, it is actually like cheap. It is like not more expensive to explore for it than it is for natural gas, and the cost of energy from hydrogen, if it's natural, it is just like way lower than green hydrogen. And so kind of producing hydrogen from like exploring for methane essentially, or exploring just for hydrogen, would be like a similar cost. But then if you also get your hydrogen by splitting the methane, that is actually additional cost. So just finding it straight up, like as it is now, if I found right now some hydrogen, it would be like a very profitable thing immediately. So it doesn't really rely on like subsidies. It doesn't really rely on like the government having to sort of provide some kind of special infrastructure. So it is something that essentially, like at the scale that we have now, it is like immediately profitable because it can already compete with hydrogen from hydrocarbons. And then in terms of like, if hydrogen, if we're going to have some kind of level of hydrogen economy, if our demand is going to increase from where it is now, then there can be all this thinking about exactly like how we're going to integrate it and how much is it going to cost and how does it compare to alternatives, say like just electrifying things. Yeah. But yeah, I think like the cool thing about it is like for right now, like it just makes sense economically as it is.
Yeah. We're running over time, and I need to let you get back to your day job, which is actually kind of this, right?
Looking for hydrogen.
So looking for hydrogen, exactly. And I don't know, because I know this is something that you're working for a kind of newly incorporated company, and it's kind of a little bit under wraps. But I think it's kind of important to get the message across that this is not just an academic discussion. Like there are people who are looking for this. You're one of them. I don't know how much you can say about what you're doing. Like, are you shipping out to different countries, or are you kind of on your laptop trying to like look at, I don't know, read through papers of where hydrogen's been spotted? Like, how does it work? Yeah.
Yeah. So yeah, I mean, it is really exciting. So I have been in academia. I've been a postdoc for like last 4 years, and I've just started now working in this new startup that is, super new, and it is very exciting. And right now, I am the only employee other than the founders and the board, and which is very exciting. We were just starting it, but yeah, essentially and the idea has been just as I've been talking about this academic research, there is like a lot of knowledge in the academic community of like how hydrogen is produced, where we can find it, and it just has always like we have studied it from like a really like different perspective with like really different questions in mind. And now that like it just sort of happens so that it has attracted a lot of attention generally as a field. um yeah, like all sort of like senior academics have like just had a lot of interest from the industry for advice and consultancy and consulting and things like that of like how can we find hydrogen. So the startup essentially is a product of that, is a sort of and I could like it's a spin out company from research at Oxford University and other universities, where we academics are we're like, well, I think we have a pretty good idea, actually probably better than there's other people of where we can find hydrogen, and we're gonna just do it ourselves. So yeah, the work that I'm doing right now, it is essentially a kind of like a data driven approach that we are assessing all kinds of evidence in terms of data that's freely available, or in literature or in various data sets that you can sort of find of essentially trying to build like both like a model, like conceptual model of like how what is not only the generation but kind of the preservation and trapping conceptual model that is kind of like a little bit similar to what has been developed in the hydrocarbon industry for oil and gas. There's this kind of concept of where we need to look. So we're building that, as well as kind of assessing the entire world for where we think it would be a good idea to go look for it. And once we make those decisions, we're gonna go and do it.
Oh, that is it. Yeah, that's cool. So yeah, you will be. Hopefully, you'll end up going somewhere nice, sunny, rather than sort of. Yeah, but that's super exciting. Yeah, this has been really eye-opening. I mean, I've always been a little bit skeptical about the hydrogen economy, but I think you've made some really good points. I mean, one is just like there's a lot of stuff where we're using hydrogen already, we can replace it. And I think it is a game changer in the equation if we can, create that hydrogen or obtain that hydrogen without having to consume other electricity, which could be energy that could be used for other things. So yeah, this is really exciting, completely groundbreaking, literally. Yeah. I don't know if you have any final thoughts, anything you'd like to share, maybe a call to action for more geologists now to kind of repair the damage that has historically been.
A lot to answer for. Yeah, no, I think it is just like what has been really motivating for me with all of this work. CO2 storage or this exploration of hydrogen is that there are things that we can do, in a kind of proactive way of trying to find solutions. And I know there's, a lot of people working on all kinds of solutions, and I think it's just really cool. And like, none of them, like, I guess, like what I find a lot in all kinds of discussions and articles is where you have some kind of technology and then it's being compared to a different technology and be like, oh, this one can't do it, it's the other one that will have to do it because it's kind of better. But I guess, like, I just have this like really agnostic kind of approach to it. Sort of really doesn't matter of, like what we end up using in decarbonizing the economy, and it's just like whatever turns out to be most optimal, and we need to work on all of those things and then find out which one is most optimal, where. And say with the hydrogen economy, like, I think it is probably true that, if we are thinking about replacing gas networks in, natural gas and hydrogen, there are a lot of like kind of there are a lot of risks, and especially like a lot of infrastructure kind of, you do actually have to replace like a lot of the pipeline because because it isn't, it leads to like embrittlement of steel. And so, it is like a good idea, and then you have to do some feasibility studies and then maybe conclude that actually this is not the best way to use hydrogen, let's use something else for this, and then like let's find the best way to use hydrogen where it is the most optimal. So yeah, I think in all of those things, like all of those things, are part of the solution. Like, and it's just exactly like doing research and then finding what's the best way to do them, and then it's going to fall into place like what makes sense in actual application of how to deploy them, because it is like such a huge task of decarbonizing entire economy, and it's going to just by default require so many like different small applications in different areas.
Yeah, I think that's right. Like a kind of no holds barred approach. And I think one thing that I've learned from, looking at the progress over the last decades is that it's not obvious ahead of time what's going to work. Like, again, like we've learned so much from deploying, like renewable energy has dropped beyond, the cost of producing renewable energy has dropped beyond their expectations. And it's just because we've learned every time we've produced, like every time we've built a factory or, produced more a batch of panels, like things have been learned. And, that's happened. That's not just happened with solar panels. I always use that example, but it's been happening with battery technology. It's been happening with wind, electrolysis. I think it will happen there, and fuel cells, it will happen there, as long as, so we shouldn't close off any of these approaches. And I'm excited to see, like, this is a very nascent one. This is a completely new thing, and it could lead anywhere. We'll see.
Yeah, no, I think that's a really exciting thing for me because, again, like, we have like very good evidence to think there is hydrogen, but there's a lot of uncertainty about how much we can find. Maybe we can find something that's like locally significant, and then we can like have some clean energy locally. Maybe we can find something that's hugely significant globally, and like there's kind of no downside, because also like in the very worst case that we kind of find out that, oh, there isn't economically feasible, it's just then, we invested some money to test out this concept and we have an answer and we can move on to something else, right? So it just makes sense to like explore all avenues where you have evidence to think that it could be really significant.
Indeed. And on that note, I think I need to let you get back to doing just that, exploring. But this has been so much fun. Thanks so much, Ruta.
Thank you so much. Yeah, it's been great to talk to you.